Hello everyone, welcome to this video on classical mechanics. In this video, let us first answer this question that given a cyclic coordinate in Lagrangian, will that cyclic coordinate be also cyclic in the corresponding Hamiltonian? So for that, what we do, we first assume that this coordinate qj, the generalized coordinate qj, that is cyclic coordinate in the given Lagrangian. What does that mean? That means that when you take the partial derivative of Lagrangian with respect to that coordinate, it comes out to be 0. That means you can ignore this particular coordinate when treating this Lagrangian L. So now we say this corresponding element qj that does not appear in the Lagrangian. Therefore, when you calculate del L by del qj, that comes out to be 0. And moreover, we know what is this del L by del qj, that is equivalent to pj dot, and you also know del L by del pj, that is equal to qj. P dot over here, right? So these two expressions we already know. From these expressions we got pj dot is equivalent to 0. That means when you integrate this thing, you will get, with respect to time, you will get pj as some constant. So the corresponding momentum coordinate is a constant over here. So moreover, using the Hamilton's canonical equations of motion, right, what do we have? We have this equation. The first equation is qj dot, that is equal to del h by del pj, and the second equation is this one, pj dot, that is equivalent to minus del h by del qj, right? So here we have this equation, and we know from previously, because this qj is given to be a cyclic coordinate, that means pj dot is 0. So if pj dot is 0, so this quantity is also equal to 0. If this quantity is equal to 0, that means we are saying in the corresponding Hamiltonian h, the coordinate qj will not appear, and hence it would be cyclic coordinate. So you saw, whenever you have any element, any coordinate, generalized coordinate, which is cyclic coordinate in Lagrangian, then it is also cyclic coordinate in the corresponding Lagrangian. In fact, we have this situation that if, say, out of these n coordinates, say, let us assume this q2 coordinate is cyclic. So in that case, we would only be requiring this q1, q3, not q2. q2 is missing from here. Note that q2 is missing, and we have q1, q3 up to qn, and then all the generalized velocities including q2 dot and time. So these are all the coordinates on which the corresponding Lagrangian operator is depending on, right? So in total we had, if we ignore this t, so in total we would have n generalized coordinates and n generalized velocities, that means 2n total, and now we are lacking one coordinate q2, that means overall 2n minus 1 coordinates are there in this Lagrangian. But talking the same in Hamiltonian, if our coordinate q2 is cyclic, that means this quantity is 0 by definition, and accordingly this is what? This is nothing but p2 dot, and this is equal to 0. That means this p2 is constant. So here the Hamiltonian is represented in the forms of generalized coordinates as well as generalized momentas. So here you see we have q1 and not q2. q2 is missing from here. q3 up to qn, right? Similarly, we have p1, and instead of p2 we have some constant over here. Let's say if I call this as alpha, so this is p1 comma alpha comma p3 up to pn and t. So basically you'll say, because alpha is a constant, so now we are in accordance with this cyclic coordinate, one cyclic coordinate, two variables are minimized. That means we are only left with 2n minus 2 variables if you ignore this t. So in total we have 2n minus 2 coordinates. Thus a cyclic component would be more profitable in Hamiltonian approach rather than using the Lagrangian approach. So this is one advantage of cyclic coordinates, which is seen more profoundly in using the Hamiltonian approach. In fact, there's this result saying if we have to solve any mechanical problem, so what we do, we have some old coordinates consisting of generalized coordinates and generalized momenta, right? And these are how many? They are j varies from 1 to n, that means they are total to n in number, and the corresponding Hamiltonian is represented by the symbol h over here. So what we do, we shift this old coordinates to a new coordinates where our generalized coordinates changes from small qj to capital Qj, and the generalized momenta changes from small pj to capital Pj, and the corresponding Hamiltonian changes from h to h dash, say, for the sake of notation, right? So here, in doing so, in converting this older coordinates to a newer set of coordinates, what we are doing this in such a manner that all of these new coordinates, that means all of these qj's, they are cyclic. So you see, if you do such a transformation from this coordinates to this kind of coordinates where all the coordinates are cyclic, that means your calculation becomes immensely lesser in comparison to to the ones which you perform here in the older coordinates. So that means we are saying our qj's in the newer coordinates, they are cyclic. So the corresponding momentum, they are all constants. Why? Because again, using the same relation, because qj are cyclic, that means del h dash. Why h dash? Because now we are in the newer coordinates and the Hamiltonian over here is h dash. So del h dash with respect to this qj, that is equivalent to 0 by definition of cyclic coordinate. And what is this quantity? This quantity is equivalent to pj dot. So pj dot over here is 0, that means all pj's, they are constants. So ultimately our Hamiltonian in the older coordinates qj and pj, small qj and pj, they are equivalent to writing it as h dash, capital qj and capital pj, right? That means we have changed our basis set from these canonical coordinates to these set of canonical coordinates. And moreover, because we are saying in this newer system all qj's, they are cyclic, that means we are only left with that means these coordinates, they are ignorable coordinates, right? And we do not find them in Hamiltonian, as where this Hamiltonian is now a function of generalized momentas only. And moreover, what are these generalized momentas? They are some constants, and we have labeled them as alpha 1. So that means the Hamiltonian, the new Hamiltonian h dash, now depends upon alpha 1, alpha 2 up to alpha n. So this is the change in the corresponding Hamiltonian. So basically the new Hamiltonian's canonical equations, they give you the solution in this newer set of coordinates, and the solution would be qj dot, that would simply be equal to del h dash by del pj, capital Pj, right? H dash is the new Hamiltonian, so we have used this notation. Now pj is constant as wj, so we have replaced this thing, and when you take the derivative of the new Hamiltonian with respect to some constant, it would again be the function of that same constant. So you saw that we started from qj dot and we reached at some constant. So basically this thing is equal to constant, and when you integrate this, you will get a linear function of time. So you will get the new generalized coordinate as a linear function of time using this transformation. So basically you got your answer, the equation of motions in this newer set of coordinates, just in a line or two. That means our calculation here becomes so easy when you transform from one coordinates to another set of coordinates. The another set of coordinates obviously include the coordinates which are all cyclic. So this is the solution in the this was the old set of coordinates, and this is the new set of coordinates. right? You have transformed this to here to here. Now what you have to do, you have to back transform to the older coordinates. Why? Because we wanted a solution in terms of those coordinates only. So what we do, we back map all the solution, whatever the solution that we obtained, we again convert the solution into the forms of small qj and small pj. Why? Because these were the things that we with which we started. That means you have to again apply these kind of equations. So qj, they are functions of capital qj and capital pj, and then small pj, they are the functions of capital qj and capital pj. So these kind of equations you again have to apply, right? So here we are introducing a notation called canonical transformation. So basically whatever transformation we were applying from the older set of coordinates to this newer set of coordinates, that transformation, this one, that is known as canonical transformation. Why this is known as canonical transformation? Because here the basis set that includes generalized coordinates and generalized momentum. So basically we are in the phase space, and so these coordinates, if you remember, we call these coordinates as canonical coordinates. Therefore, the corresponding transformation is also known as the canonical transformation. Moreover, these transformations are taking place in the phase space. Why? Because in phase space, the set of bases that are the generalized coordinates, the generalized momentas, right, and not the generalized momentums and the generalized velocities. So this thing was not there. So we are dealing these transformation in the phase space. Moreover, the Hamiltonian, this is the property of such transformations, that the Hamilton's equations, they remain invariant under such transformations. So that is an introduction to what are canonical transformation. In the next video, we'll build upon these transformations in more detail. Well, that is it for this video. Thank you for watching.